There exists a region of space where the universe appears to have forgotten itself. A place so vast and so empty that it challenges the very foundations of what existence should look like according to the mathematical models that describe cosmic structure formation. This is not a dramatization. This is not speculation crafted to provoke wonder. This is an observational fact derived from decades of astronomical measurement, and it sits uncomfortably within the framework of understood physics. Before proceeding further into what this documentary will examine, a simple invitation extends to those watching. Full screen allows the scale of what follows to register more completely. Subscription ensures access to future examinations of phenomena that resist easy categorization. These are not demands, merely observations about how information reaches human perception most effectively in an age of fractured attention. What follows now is a journey into one of the most profound mysteries that telescopic observation has yet encountered, and it requires no embellishment beyond the facts themselves. The Boötes Void is a name that carries within it both a location and a profound absence. Boötes, the herdsman constellation, traces an ancient pattern across the northern celestial hemisphere, recognizable to cultures separated by oceans and millennia. Within the three-dimensional space that lies in the direction of this constellation, at a distance of approximately 700 million light-years from Earth, there exists a region that defies the statistical expectations of cosmic structure to such a degree that its very existence posed immediate theoretical challenges upon discovery. To understand why this void represents something more than simply empty space, one must first understand what empty space should look like in a universe governed by the principles of gravitational collapse, dark matter distribution, and the hierarchical assembly of structure from primordial density fluctuations. The universe is not uniform. This fact, seemingly obvious to any observer of the night sky, represents one of the most important discoveries in cosmological science. The cosmic microwave background radiation, the afterglow of the Big Bang itself, shows temperature variations on the order of 1 part in 100,000. These tiny fluctuations, quantum mechanical in origin, stretched to cosmic scales by inflation, seeded the growth of all structure that would follow. Regions with slightly higher density possessed slightly stronger gravitational fields. Matter flowed toward these regions. The rich grew richer. The poor grew poorer. Over billions of years, this process of gravitational instability transformed nearly smooth initial conditions into the cosmic web, a filamentary network of galaxy clusters connected by tendrils of matter, with vast voids between them. Voids are not unexpected. They are, in fact, a necessary consequence of structure formation. When matter collapses into overdense regions, it must be drawn from somewhere. The regions it leaves behind become underdense. These regions expand faster than the cosmic average because they contain less matter to slow their expansion through gravitational attraction. Voids grow with time. Computer simulations of cosmic structure formation based on the lambda cold dark matter model, which incorporates dark energy and cold dark matter as the dominant components of cosmic mass energy, produce void networks that bear remarkable resemblance to observations. The universe appears, at the largest scales, to resemble foam or a sponge, with galaxies concentrated along the surfaces of bubble-like structures and vast empty regions in between. The typical void has a diameter of perhaps 10 to 30 megaparsecs. A megaparsec represents approximately 3.26 million light-years. The local void, which lies adjacent to our own local group of galaxies, measures roughly 30 megaparsecs across. Voids of this scale are common features of cosmic structure, predicted by theory and observed throughout the universe. They contain fewer galaxies than average, but not zero. Small dwarf galaxies, isolated systems that never participated fully in the clustering hierarchy, can often be found scattered within voids. The darkness of voids is relative, not absolute. The Boötes Void is different. When Robert Kirshner and his colleagues at the University of Michigan conducted a redshift survey in 1981, mapping the three-dimensional distribution of galaxies by measuring how much the expansion of the universe had stretched the wavelength of their light. They encountered a region where galaxies simply ceased to appear. The survey method involved selecting galaxies from photographic plates, measuring their spectra to determine redshift, and plotting their positions in a volume of space. As data accumulated, patterns emerged. Galaxies clustered. Filaments connected clusters. Voids appeared between the filaments. This was expected. What was not expected was the scale of the void that materialized in the direction of Boötes. The Boötes Void spans approximately 330 million light-years in diameter. Expressed in megaparsecs, this translates to a radius of approximately 62 megaparsecs. This dimension places the void in a category called supervoids, structures significantly larger than typical voids. Size alone, however, does not constitute the anomaly. The critical feature that elevates the Boötes Void from merely large to physically puzzling is the extreme nature of its emptiness combined with the specific character of the small amount of structure that does exist within it. Within a spherical volume 330 million light-years across, statistical expectations based on the average density of galaxies in the universe suggest that approximately 2,000 galaxies should be present. This is not a rough guess. This is a calculation based on decades of deep sky surveys that have cataloged millions of galaxies and established the mean number density of galaxies in the cosmos with considerable precision. The distribution of galaxies is not perfectly smooth, even outside voids. There are fluctuations. Clusters contain more galaxies than average. Voids contain fewer. But these fluctuations follow statistical patterns. The number of galaxies in a randomly selected volume of a given size will vary, but the variation follows predictable distributions around the mean. The Boötes Void contains approximately 60 galaxies, not 2,000. 60. This represents a deficit of more than 97%. The probability of such an extreme underdensity arising by chance from the statistical fluctuations that characterize normal cosmic structure is vanishingly small. This is not merely an empty region. This is a region that is empty to a degree that demands explanation beyond the standard mechanisms of void formation. Galaxies are luminous because they contain stars. Stars form from gas. Gas collapses under gravity. The presence of even a small number of galaxies within the void indicates that matter exists there. The void is not a true vacuum, nor is it a region from which all matter has been expelled. It is, instead, a region in which the matter that is present has failed to collapse into galaxies at the rate and efficiency seen elsewhere in the universe. This distinction is critical. The question is not where the matter went. The question is why the matter that remains did not form galaxies. The 60 galaxies that do exist within the Boötes Void are not randomly distributed throughout its volume. They occupy a tube-like structure that runs through the central region of the void. This filamentary or cylindrical arrangement of galaxies is, on the surface, reminiscent of the filamentary structure of the cosmic web itself, where galaxies trace out the walls and filaments between voids. But the Boötes structure is embedded within a void, not defining its boundary. It is a filament within an absence, a thread of light through darkness. The tube structure contains galaxies with measured properties that do not appear drastically different from galaxies found in higher density regions. Spectroscopic analysis reveals emission lines characteristic of star formation. Metallicity measurements, which trace the abundance of elements heavier than hydrogen and helium, indicate chemical enrichment consistent with ongoing stellar nucleosynthesis. These galaxies are not primordial relics frozen in an early evolutionary state. They are active star-forming systems. Their existence within the void is not a matter of these galaxies being somehow fundamentally different in character, but rather a matter of their extreme rarity in this specific location. The discovery of the Boötes Void occurred during a period when cosmological models were still being refined, but even with the uncertainties of the time, the void's properties were immediately recognized as unusual. Early theoretical work attempted to explain the void through the merger of multiple smaller voids, a process analogous to the coalescence of soap bubbles. Small voids in a foam structure can merge when the thin walls between them dissolve, creating larger voids. Applied to cosmic structure, this would mean that multiple ordinary-scale voids happen to form adjacent to one another, and, over time, the galaxies and matter along their boundaries migrated outward, leaving a single large merged structure. This merger hypothesis has the advantage of being consistent with known physics. Voids expand. If several voids expand into one another, a supervoid results. Computer simulations of structure formation do produce occasional large voids through this mechanism. However, the simulations also make predictions about how often such structures should appear and about the residual structure that should remain within them. The frequency of Boötes scale voids in simulations is low, but not zero. A handful of such structures might be expected within the observable universe. The existence of one large void is not, by itself, impossible according to lambda cold dark matter cosmology. The challenge emerges when examining the details. The extreme nature of the emptiness, the specific reduction to 60 galaxies rather than a few hundred, and the peculiar tube-like arrangement of those galaxies, all push against the boundaries of what simulations naturally produce. Lambda CDM is a statistical theory. It predicts distributions of structure, not the exact configuration of every galaxy. Within the statistical ensemble of possible universes consistent with lambda CDM, universes containing Boötes-like voids exist, but they are rare within that ensemble. The question becomes whether the observed properties of the Boötes void fall within the expected range of rare but possible outcomes, or whether they represent an outlier so extreme that it suggests something beyond the standard model is at work. To address this question rigorously requires understanding not just that the void is large and empty, but why it became so large and so empty in the context of structure formation physics. The growth of structure from initial conditions proceeds through well-understood gravitational dynamics modified by the expansion of space. In the early universe, when the cosmos was denser and hotter, matter and radiation were coupled. Photons scattered off electrons in the primordial plasma, creating pressure that resisted gravitational collapse of ordinary matter. Dark matter, which does not interact with photons, could begin collapsing earlier. By the time the universe cooled enough for electrons and protons to combine into neutral hydrogen, approximately 380,000 years after the Big Bang, dark matter had already begun to form the gravitational potential wells into which ordinary matter would fall. These dark matter halos grew hierarchically. Small halos formed first. They merged to form larger halos. Gas fell into halos, cooled, and formed stars. Galaxies assembled within the halos. This process was not uniform across space because the initial density fluctuations were not uniform. Regions that began slightly denser than average collapsed earlier and more vigorously. Regions that began slightly less dense than average collapsed later and less vigorously. The rich got richer faster. Voids are regions that started slightly underdense and remained so. As matter flowed toward overdense regions, underdense regions became more underdense. The expansion of space, driven by dark energy, accelerated this process. In an overdense region, gravity slows the expansion, allowing structure to collapse. In an underdense region, gravity is weaker, and the expansion proceeds faster, pulling apart any structures that might try to form. This is a feedback process. Underdensity leads to faster expansion, which leads to greater underdensity, which leads to even faster expansion. In a normal void, this process produces a region containing perhaps 10 to 30% of the average galaxy density. The void expands, but it does not empty completely because the initial underdensity was not extreme, and because there are still small-scale density fluctuations within the void that can collapse locally to form dwarf galaxies. The Boötes void, with only 3% of the expected galaxy count, suggests an initial underdensity far more extreme than typical, or some process that suppressed galaxy formation within the void more efficiently than standard models predict. One hypothesis invokes the properties of dark energy. Dark energy, the component of a universe driving accelerated expansion, is typically modeled as a cosmological constant, a perfectly uniform energy density of empty space itself. But dark energy could, in principle, be dynamical, varying in strength from place to place or over time. If dark energy were stronger within the region that became the Boötes Void, it would drive expansion more aggressively, preventing matter from collapsing into galaxies, even in regions with near-average initial density. This is an attractive hypothesis because it provides a mechanism to explain the extreme emptiness without requiring an impossibly rare initial underdensity. However, current constraints on dark energy from cosmological observations strongly favor a cosmological constant with no significant spatial variation. The temperature fluctuations in the cosmic microwave background, the distances to supernovae at various redshifts, the clustering of galaxies on large scales, and the patterns in the distribution of matter inferred from gravitational lensing all point toward dark energy that behaves consistently across the observable universe. Introducing significant spatial variation in dark energy to explain the Boötes Void would create inconsistencies with these other observations unless the variation were confined to scales smaller than those probed by most cosmological tests, which would require fine-tuning. Another hypothesis examines the role of dark matter itself. Cold dark matter, the type assumed in lambda CDM, consists of particles that move slowly compared to the speed of light and interact only through gravity. This allows dark matter to clump efficiently on all scales. If dark matter were instead warm or hot, meaning the particles move at relativistic speeds, they would stream out of small scale over densities, preventing the formation of structure below a certain mass scale. In a region where dark matter properties differed from the cosmic average, galaxy formation could be suppressed. But like the dark energy variation hypothesis, this requires dark matter to have properties that vary spatially, which is not supported by observations of structure formation elsewhere in the universe. A third line of inquiry considers whether the initial density fluctuations in the region that became the Boötes Void were configured in a specific way that is rare but not impossible within the expected spectrum of primordial fluctuations. Inflation, the rapid exponential expansion of a universe in its first fraction of a second, stretched quantum fluctuations to macroscopic scales. These fluctuations are typically assumed to follow a Gaussian random distribution with a nearly scale-invariant power spectrum. Most of the statistical properties of the cosmic microwave background and large-scale structure are consistent with this assumption. However, there could be rare, non-Gaussian features, localized regions where the fluctuations were configured unusually. A localized region of extreme underdensity in the primordial density field would grow into a large void. The challenge with this explanation is quantifying exactly how rare the required initial configuration would be, and whether it falls within the expected range given the volume of the observable universe. The observable universe contains a finite number of independent regions on the scale of the Boötes Void. If the probability of the required initial configuration is 1 in 10, and there are 100 independent regions, then finding one such structure is unsurprising. If the probability is 1 in a million, and there are only 100 regions, then finding one is evidence that something beyond the standard model is influencing structure formation. Calculating this probability precisely requires running a large ensemble of simulations with different random realizations of initial conditions drawn from the expected spectrum of fluctuations and counting what fraction of simulated universes produce Boötes-like voids. Such simulation campaigns have been conducted, and the results indicate that voids as large and as empty as the Boötes Void are at the tail of the distribution. They are rare, appearing in perhaps a few % of simulated universes, but not so rare as to be impossible. This places the Boötes Void in an ambiguous category. It is unusual enough to provoke scrutiny, but not so unusual that it definitively rules out lambda CDM. The ambiguity is deepened by the tube structure. The filamentary or cylindrical arrangement of the 60 galaxies within the void is not easily explained by void merger models. When voids merge, The galaxies along the former boundaries of the merging voids do not typically rearrange themselves into a coherent tube through the center of the resulting supervoid. They would more naturally be expected to remain on the periphery or to form multiple disconnected clumps scattered throughout the volume. The presence of a single coherent structure suggests that the tube represents a residual filament from the cosmic web that happened to pass through the region that became the void. Filaments in the cosmic web are regions where matter flows along preferred directions, channeled by the gravitational potential wells of dark matter halos. A filament is not a uniform structure. It consists of dark matter halos strung out along a line, with galaxies forming within those halos. If a filament happens to pass through a region that is otherwise underdense, the filament itself could remain relatively intact even as the surrounding volume expands and empties. This would produce exactly the observed configuration, a tube of galaxies embedded in a void. For this to occur, the initial density field must have contained a specific geometric configuration, a filamentary overdensity passing through a large underdense region. Such configurations are not forbidden by inflation, but they require a particular alignment of fluctuations on different scales. Small-scale fluctuations create filaments. Large-scale fluctuations create voids. Normally, these operate independently in different regions. For a filament to pass through a void requires the filament and the void to be spatially coincident, which is a low-probability event. Once again, the question becomes whether this is rare enough to be surprising. The observable universe is large. Low-probability events happen somewhere. The Boötes Void is famous precisely because it is unusual. There is a selection effect at work. Astronomers discovered the void because it is extreme. Less extreme voids are common and unremarkable. The existence of one extreme case in a large volume is not necessarily evidence of new physics. It could simply be the high tail of the statistical distribution. But there is a subtlety here that demands careful consideration. The selection effect argument applies to discovering something unusual. It does not, by itself, explain why the unusual thing has the specific properties it does. Discovering a large void is one thing. Discovering a large void with a tube structure is another. Discovering a large void with a tube structure containing exactly 60 galaxies is yet another. Each additional constraint reduces the probability space. If every additional detail of the Boötes void can be shown to be consistent with lambda CDM given a sufficiently rare but not impossible initial condition, then the void remains a curiosity rather than a crisis. If even one detail cannot be accommodated, then the void becomes evidence of something beyond the standard model. To evaluate, this requires detailed comparison between observations and simulations. The observed properties of the Boötes void must be quantified precisely. The diameter of the void, the number and spatial distribution of galaxies within it, the morphologies and colors of those galaxies, the star formation rates, the metallicities, the kinematics, all must be measured. Then, simulations must be run with sufficient volume and resolution to capture the formation of rare large voids, and the properties of those simulated voids must be compared statistically to the observations. If the observed Boötes void falls within the distribution of properties exhibited by simulated voids, it is consistent with lambda CDM. If it falls outside that distribution, it is not. Such comparisons have been conducted, and the results are mixed. Some properties of the Boötes void fall comfortably within the range of simulated voids. Other properties lie at the edge of the distribution. No single property definitively rules out lambda CDM. But the combination of properties, the fact that multiple features are simultaneously at the tail of their respective distributions, is statistically unusual. When evaluating the probability of multiple rare events occurring simultaneously, the individual probabilities multiply, driving the combined probability lower. If the void size is a 1 in 10 event, and the emptiness is a 1 in 10 event, and the tube structure is a 1 in 10 event, the combination is a 1 in 1,000 event. With enough independent structures in the observable universe, a 1 in 1,000 event might still be expected somewhere. But if each feature is more like 1 in 100, the combination becomes 1 in a million, and finding even one such structure in the observable universe becomes genuinely surprising. Quantifying these probabilities precisely is complicated by systematic uncertainties in both observations and simulations. Observations are limited by telescope sensitivity, sky coverage, and the difficulty of obtaining spectroscopic redshifts for faint galaxies. Some galaxies within the Boötes Void may exist, but remain undetected. If the true number of galaxies is not 60, but 600, the deficit becomes less extreme, and the void becomes less unusual. However, deep follow-up surveys of the Boötes Void have been conducted with sensitive instruments, and the galaxy count has not increased dramatically. The void remains substantially emptier than expected, even after accounting for possible incompleteness. Simulations are limited by computational resolution and by uncertainties in the physics of galaxy formation. Simulating the entire formation history of structure from the Big Bang to the present requires resolving scales from hundreds of megaparsecs down to individual galaxies, a dynamic range of many orders of magnitude. This is computationally expensive. Compromises must be made. Large volume simulations that capture the formation of rare large-scale structures sacrifice resolution, meaning they cannot accurately model the formation of individual galaxies. High-resolution simulations that model galaxies in detail sacrifice volume, meaning they do not contain rare large-scale structures. Bridging this gap requires either enormous computational resources or approximate methods that introduce additional uncertainties. Galaxy formation physics itself is complex and incompletely understood. Dark matter simulations are relatively straightforward because dark matter interacts only through gravity, which is well understood. But galaxies are made of ordinary matter, which experiences gas pressure, radiative cooling, star formation, supernova feedback, black hole growth, and feedback from active galactic nuclei. These processes operate on scales far smaller than the resolution of cosmological simulations and must be modeled using subgrid prescriptions, approximate rules calibrated to match observed galaxy properties. Different prescriptions produce different predictions for the abundance and properties of galaxies in voids. If galaxy formation is suppressed in underdense regions more strongly than some models predict, the Boötes Void could be accommodated within lambda CDM, even if its extreme emptiness initially appears anomalous. This highlights a fundamental challenge in cosmology. Observations provide one universe. Simulations provide many possible universes, but those universes depend on assumptions about initial conditions, dark matter properties, dark energy properties, and galaxy formation physics. Comparing one observed universe to an ensemble of simulated universes allows conclusions about whether the observed universe is typical or atypical within the ensemble. But the ensemble itself is only as reliable as the assumptions that generated it. If the assumptions are correct, an atypical observed universe suggests the need for new physics. If the assumptions are incorrect, an atypical observed universe merely indicates that the assumptions need refinement. The Boötes Void sits in this uncertain territory. It is atypical enough to demand explanation, but not so atypical that it unambiguously requires new physics. Resolving this ambiguity requires either more data or better simulations or both. More data means deeper surveys that could reveal additional faint galaxies within the void, or that could identify other Boötes-like voids elsewhere in the universe. If the Boötes Void is truly unique, its existence is more surprising than if multiple similar structures exist. If multiple exist, they can be studied as a population, and their collective properties can be compared to simulation predictions with greater statistical power. Better simulations mean larger volumes with higher resolution, allowing rare large-scale structures and individual galaxies to be captured simultaneously. Improvements in computational power and algorithmic efficiency are making such simulations increasingly feasible. Beyond these technical considerations, the Boötes Void provokes deeper questions about the nature of cosmic structure and the role of rare events in cosmology. The universe is a single realization of a stochastic process. The initial conditions set by inflation were drawn for a probability distribution. The particular realization of those initial conditions that occurred in our universe led to the specific arrangement of galaxies, clusters, filaments, and voids we observe. A different realization would have produced a different arrangement. In that sense, every specific feature of the observed universe, including the Boötes Void, is a rare event. The exact configuration of matter in any given location is unique and unlikely. But cosmology is not concerned with predicting exact configurations. It is concerned with predicting statistical properties. The theory does not predict where each galaxy will be. It predicts how many galaxies exist, how they are clustered, how their properties vary with mass and environment. These statistical predictions can be tested against observations, even though each specific galaxy is unique. The Boötes Void becomes relevant when its properties are sufficiently extreme that they push the boundaries of the statistical distributions predicted by the theory. This raises a philosophical question about the threshold for claiming evidence of new physics. If a feature is at the 1 percentile of the predicted distribution, is it evidence? At the 1 in 1,000 tail? At 1 in a million? There is no universal answer. The threshold depends on context, on how well the theory is established by other observations, on how confident we are in the systematic uncertainties, on how much we trust the simulations. Cosmology does not operate with the controlled experiments and reproducibility of laboratory physics. It operates with one universe, observed once, with a theory that makes probabilistic predictions. Claiming new physics requires confidence that the observation is genuinely inconsistent with the theory, not merely rare within the theory. The Boötes Void has not reached that threshold in the majority view of the cosmological community. It is widely regarded as a remarkable structure, worthy of study, at the edge of what lambda CDM naturally produces, but not definitively outside it. However, this majority view is not unanimous, and it evolves as new data and new simulations become available. Some researchers have argued that the combination of the void's size, emptiness, and tube structure does represent a genuine tension with lambda CDM that has been underestimated due to conservative statistical approaches. Others have argued that the void is comfortably explained once proper account is taken of systematic uncertainties and selection effects. This ongoing debate underscores a critical aspect of modern cosmology. The field operates at the frontier of what is empirically knowable. The observable universe is finite. The number of independent large-scale structures it contains is limited. Statistical tests are limited by this finite sample size. Unlike particle physics, where trillions of identical collisions can be conducted to measure properties with exquisite precision, cosmology must extract conclusions from a single universe. Every measurement is a balance between the strength of the signal and the uncertainty in the measurement and the model. The tube structure within the Boötes Void deserves additional scrutiny because it represents the most concrete feature that deviates from naive expectations. Void can be large. Voids can be empty. But voids with coherent internal structure are harder to explain. The 60 galaxies are not scattered randomly throughout the void's volume. They form a filament. Filaments are features of the cosmic web, formed where multiple clusters are gravitationally connected. But the cosmic web forms in regions where matter is present. The Boötes Void is defined by the absence of matter. A filament within a void is, in a sense, a contradiction, a thread of structure in a region where structure should not exist. One way to reconcile this is to argue that the void is not a simple spherical underdensity, but a more complex shape. If the underdense region is shaped like a toroid or a shell, with a less underdense channel through the middle, then the galaxies observed in the tube are not inside the void, but rather in the channel where the void's density is slightly higher. This would make the tube structure less anomalous, simply a line of slightly higher density in a much larger region of lower density. However, observations do not clearly support a toroidal or shell-like morphology. The void appears roughly spherical in redshift surveys, and the tube passes through its central region, not along an edge. Another possibility is that the tube represents the remnant of a filament that predated the void's formation. If a filament existed in the initial density field and a void expanded around it, the filament could persist if the overdensity along its length were sufficient to resist the expansion. This requires a delicate balance. The filament must be overdense enough to hold together against the outward expansion of the void, but not so overdense that it draws matter from the surrounding region and fills the void. Such a balance is possible in principle, but represents a fine-tuned configuration unlikely to arise by chance. Yet another interpretation invokes the dynamics of void expansion. As a void grows, matter along its edges is pushed outward by the expansion. But the expansion is not perfectly uniform in all directions. Deviations from spherical symmetry, driven by the asymmetric distribution of surrounding structures, can focus matter along particular directions. If the expansion of the Boötes void happened to focus matter inward along one axis, creating a tube-like distribution, this could explain the observed structure. However, simulations of void expansion do not generically produce such strong focusing. The resulting structures are typically more irregular and less coherent than the observed tube. Each of these explanations relies on invoking specific configurations or processes that are possible within lambda CDM, but rare. The cumulative improbability of all the required conditions is what makes the Boötes void genuinely puzzling. It is not that any one feature is impossible. It is that all the features must occur together in the same location. This is the essence of the anomaly. Anomalies in cosmology have a complex history. Some have been resolved as observational artifacts, the result of incomplete data or systematic errors. Others have been resolved by refinements to theoretical models that show the anomalous feature was actually predicted once calculations were done more carefully. A few have persisted and grown into genuine crises that required new physics to resolve. The cosmic microwave background dipole, the large-scale anisotropy in the temperature of the CMB caused by our motion relative to the CMB rest frame, was initially puzzling but is now understood as a Doppler shift. The horizon problem, the fact that regions of the CMB that should never have been in causal contact have the same temperature, was resolved by the introduction of inflation. The accelerated expansion of the universe, revealed by supernova observations in the late 1990s, required dark energy, a new component of the cosmic energy budget. The Boötes void has not yet reached the status of a crisis because it is not in clear contradiction with observation. It is simply at the tail of the distribution. But tails matter. Outliers drive scientific progress. They're the places where theories are tested most stringently. A theory that explains 99% of observations but fails on the 1% is incomplete. The question is whether the Boötes void is part of the 1% that requires new physics or part of the 99% that is already explained but happens to look unusual. To approach this question from another angle, consider what new physics might explain the Boötes void if lambda CDM proves inadequate. One category of explanations involves modifications to the nature of dark matter or dark energy, already mentioned above. If dark energy varies spatially, or if dark matter has properties that differ from standard cold dark matter in specific regions, the extreme emptiness of the void could be explained. But such modifications must be consistent with all other cosmological observations, which constrains their form significantly. Another category involves modifications to gravity itself on cosmological scales. General relativity, Einstein's theory of gravity, has been tested extensively in the solar system and in binary pulsar systems. But cosmological scales represent an extrapolation of many orders of magnitude beyond these tests. It is conceivable that gravity behaves differently on scales of hundreds of megaparsecs than it does on scales of astronomical units or light years. Modified gravity theories, such as modified Newtonian dynamics or its relativistic generalizations, have been proposed to explain the rotation curves of galaxies without dark matter. Some of these theories make different predictions for the growth of large-scale structure, and could, in principle, explain the existence of unusually large or empty voids. However, most modified gravity theories that have been explored in detail face challenges in explaining the full range of cosmological observations, particularly the cosmic microwave background and the formation of structure on multiple scales simultaneously. A third category, more speculative, involves topological defects or other relics from the early universe. If the early universe underwent phase transitions, analogous to the freezing of water or the magnetization of iron, these transitions could have left behind defects in the structure of spacetime itself. Cosmic strings, domain walls, and monopoles are examples of such defect predicted in some particle physics theories. If a large defect happened to exist in the region that became the Boötes Void, it could have influenced the distribution of matter in ways not captured by standard lambda CDM simulations. However, current observations of the cosmic microwave background place very stringent limits on the abundance of topological defects. A defect large enough to influence a 330 million light-year region would likely produce observable signatures in the CMB that have not been seen. A fourth category, even more speculative, involves effects from outside our observable universe or from earlier cosmological epochs. If the observable universe is embedded in a larger multiverse, with different regions having different physical constants or different histories, then the Boötes Void could be a remnant of interaction with another region, or a scar from a pre-inflationary event. Such ideas are inherently difficult to test because they invoke phenomena beyond what is directly observable. They are not ruled out, but they lack predictive power without additional assumptions. None of these exotic explanations are necessary if the Boötes Void can be accommodated within lambda CDM, even as a rare event. The principle of parsimony, often invoked in science, suggests that simpler explanations should be preferred unless evidence definitively rules them out. Lambda CDM is a simple model with a small number of parameters that explains a vast range of observations. Abandoning it in favor of a more complex model requires strong justification. The Boötes Void, as currently understood, does not provide that justification, but it does provide motivation for continued scrutiny. Part of what makes the void compelling is its isolation. It is not merely empty of galaxies. It is surrounded by regions that are not empty. The Boötes Void is bounded by several large galaxy superclusters: the Ursa Major supercluster, the Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, and the Boötes supercluster itself. These are concentrations of thousands of galaxies clustered into groups and filaments. The contrast between these dense regions and the void is stark. The void is not simply a region that happens to be underdense. It is a region that is dramatically underdense, surrounded by regions that are dramatically overdense. This clustering void anticorrelation is expected in the cosmic web. Overdense regions and underdense regions are two sides of the same coin. Both are rising from the same initial density fluctuations. Matter that flows into overdense regions must come from underdense regions. The stronger the overdensity, the more matter it draws in, and the more empty the surrounding voids become. In this sense, the presence of large superclusters around the Boötes Void is consistent with the void's extreme emptiness. The superclusters drain the void, but this raises a question about geometry. The void is roughly spherical. The surrounding superclusters are distributed around its periphery. If matter drained uniformly from the void toward the surrounding superclusters, the residual structure within the void should be minimal and should not exhibit a preferred direction. The tube structure suggests that matter did not drain uniformly. It suggests that there was an asymmetry in the density field or in the gravitational potential that channeled matter along a particular axis. Such asymmetries are possible in principle, but again, they represent specific configurations that are rarer than generic spherically symmetric drainage. The velocity field within and around voids provides additional information. Galaxies are not static. They move under the influence of gravity, both from their own motion through space and from the expansion of space itself. By measuring the velocities of galaxies through redshift surveys and through peculiar velocity measurements that account for the Hubble flow, the underlying gravitational potential can be mapped. Voids have characteristic velocity fields. Galaxies within a void tend to move outward, away from the void center, as the void expands. Galaxies on the edge of a void move toward the surrounding overdense regions. Measurements of the velocity field around the Boötes Void are consistent with these expectations. Galaxies near the void's edge are moving away from it, drawn by the gravitational pull of the surrounding superclusters. This confirms that the void is a real underdensity in the mass distribution, not an observational artifact. However, detailed velocity measurements within the void are sparse because there are so few galaxies. The 60 galaxies in the tube do not provide enough data points to map the internal velocity field with high precision. This is a fundamental challenge. The very feature that makes the void interesting, its extreme emptiness, also makes it difficult to study in detail. Despite these challenges, the galaxies that do exist within the void have been studied individually. Spectroscopic observations reveal their redshifts, allowing their positions along the line of sight to be determined. Photometric observations in multiple wavelengths provide information about their stellar populations, ages, and star formation histories. These studies indicate that the void galaxies are not a distinct population. They appear similar to galaxies found in low-density environments elsewhere in the universe. Some are blue, indicating ongoing star formation. Some are red, indicating older stellar populations with little recent star formation. The mix of properties is consistent with what would be expected for a small sample of galaxies drawn from the low-density tail of the cosmic galaxy distribution. This similarity is, in a sense, part of the puzzle. If the void formed through some exotic process, one might expect the galaxies within it to show unusual properties, signs of a different formation history. The fact that they appear normal suggests that their formation proceeded through standard mechanisms, just in an environment where those mechanisms operated far less efficiently than usual. They're not exotic galaxies in a normal environment. They're normal galaxies in an exotic environment. The exotic nature of the environment is quantified by comparing the number density of galaxies in the void to the number density outside it. The ratio is approximately 1 to 30. For every galaxy inside the Boötes Void, there are 30 galaxies in the same volume outside. This ratio is more extreme than typical voids, which have ratios of perhaps 1 to 3 or 1 to 5. The factor of 30 deficit is what places the Boötes Void in the supervoid category and what makes it a subject of ongoing research. Another line of investigation examines the void's impact on the cosmic microwave background. The CMB, formed when the universe was 380,000 years old, carries imprints of structure that existed at that early time. But the CMB photons have traveled through billions of years of cosmic history to reach us, and that journey can be affected by the large-scale structure they traverse. One such effect is the integrated Sachs-Wolf effect, where photons gain or lose energy as they pass through gravitational potentials that are changing with time due to the expansion of the universe and the influence of dark energy. Photons passing through a void are expected to experience a net redshift because the void's gravitational potential becomes less negative as the void expands and empties. This redshift translates to a slight decrease in the CMB temperature in the direction of the void. Large voids should therefore appear as cold spots in the CMB. This effect has been observed statistically for large voids, but measuring it for individual voids requires the void to be very large and nearby, so that its angular size on the sky is substantial. The Boötes Void, 700 million light-years distance, subtends an angle of several degrees. This is large enough that an integrated Sachs-Wolf signal could, in principle, be detected. Searches for a cold spot in the CMB in the direction of the Boötes Void have been conducted, but the results are inconclusive. The CMB temperature fluctuations are dominated by primordial fluctuations from the early universe, which are much larger in amplitude than the integrated Sachs-Wolf effect from voids. Extracting the void signal requires careful statistical techniques and is limited by the cosmic variance inherent in the primordial fluctuations. Some analyses have reported a marginal detection of a cold spot associated with the Boötes Void, while others have found no significant signal. This ambiguity mirrors the ambiguity in the interpretation of the void itself. It is at the threshold of detectability, neither clearly present nor clearly absent. If a cold spot were unambiguously detected, it would provide independent confirmation that the void is indeed a large underdensity, and it would allow measurement of the void's integrated gravitational potential along the line of sight. This would complement the galaxy count measurements, which probe the distribution of luminous matter, by probing the distribution of all matter, including dark matter. A mismatch between the galaxy-based void properties and the CMB-based void properties would be significant, potentially indicating a breakdown in the relationship between luminous matter and total matter that is assumed in standard models. No such mismatch has been found, but the measurements are not yet precise enough to rule out subtle discrepancies. Future CMB missions with higher sensitivity and better angular resolution may provide clearer answers. Similarly, future galaxy surveys with greater depth and coverage will improve the census of galaxies within the void, reducing the uncertainty in the galaxy count and potentially revealing faint galaxies that have so far gone undetected. The history of the Boötes Void since its discovery in 1981 is a history of gradually increasing data quality and gradually refining theoretical interpretations. Early observations relied on photographic plates and limited spectroscopy. Modern observations use digital detectors, large telescopes, and multi-object spectrographs that can measure redshifts for hundreds of galaxies simultaneously. Early simulations were limited to small volumes with coarse resolution. Modern simulations use supercomputers to evolve billions of particles over cosmic time, capturing the formation of the cosmic web in exquisite detail. Each generation of data and simulations has sharpened the picture of the void, but it has not resolved the underlying question of whether the void represents a significant challenge to lambda CDM. The fact that the question persists after more than 4 decades of study is itself noteworthy. If the void were clearly consistent with the standard model, the question would have been settled. If it were clearly inconsistent, the standard model would have been modified or replaced. Instead, the void remains in the liminal space of being unusual enough to attract attention, but not unusual enough to force a paradigm shift. This liminal status is characteristic of many problems in contemporary cosmology. The field has achieved remarkable success in establishing a standard model that explains the universe's large-scale properties with a small number of parameters. But the precision of modern observations reveals features that push the edges of the model. Features that are not definitively wrong, but are not comfortably right. The Hubble tension, the mismatch between different measurements of the universe's expansion rate, is one example. The sigma-8 tension, the mismatch between different measurements of the amplitude of matter clustering, is another. The Boötes Void can be seen as part of this broader pattern, a specific instance of a more general phenomenon where the universe exhibits more complexity and more extreme features than the simplest version of the standard model naturally produces. Resolving these tensions requires either finding systematic errors in the observations, refining the theoretical models within the standard framework, or introducing new physics. The Boötes Void has not yet reached the point where new physics is clearly required, but it has reached the point where it cannot be dismissed as a trivial curiosity. It is a structure that demands explanation, and the explanation must account for all its properties simultaneously. The size, the emptiness, the tube structure, the surrounding superclusters, the properties of the galaxies within it, and potentially the CMB signal in its direction. One approach to resolving the tension is to search for other structures similar to the Boötes Void. If the void is unique, its existence is more surprising and more difficult to explain within lambda CDM. If multiple such voids exist, they can be studied as a population, and their statistical properties can be compared to simulation predictions with greater confidence. Several large galaxy surveys conducted in recent decades, including the Sloan Digital Sky Survey, The 2-degree field galaxy redshift survey and more recent surveys have mapped the three-dimensional distribution of galaxies over large volumes of the universe. These surveys have identified numerous voids, some of which approach the size of the Boötes Void, but none that clearly exceeded in both size and emptiness. This suggests that the Boötes Void is indeed among the most extreme structures of its kind, but it is not unique. There are other large voids. There are other empty voids, but the combination of being both very large and very empty, with a tube structure, appears to be rare. The rarity is consistent with the void being at the tail of the distribution predicted by lambda CDM, but it also means that the statistical sample of similar structures is small, limiting the power of statistical tests. Another approach is to examine the cosmic web in which the Boötes Void is embedded. Voids do not exist in isolation. They are part of a larger network of structures. The properties of a void are influenced by the properties of the surrounding filaments and clusters. By mapping the cosmic web in detail, including not just the distribution of galaxies, but also the distribution of dark matter inferred from gravitational lensing, a more complete picture of the void's formation history can be constructed. If the void formed through the merger of smaller voids, there may be residual signatures of those smaller structures in the current distribution of matter. If the void formed through some other process, the distribution of surrounding matter may reflect that process. Gravitational lensing is a powerful tool for this purpose. When light from a distant galaxy passes near a massive structure, the gravitational field of that structure bends the light's path, distorting the image of the distant galaxy. By measuring these distortions statistically over many background galaxies, the distribution of mass in the foreground structure can be inferred. This technique, called weak gravitational lensing, has been used to map the dark matter distribution in clusters and filaments. Applying it to voids is more challenging because voids have very little mass, producing only subtle lensing signals, but it is possible in principle, especially with large datasets. Weak lensing measurements in the direction of the Boötes Void could reveal whether the void is as empty of dark matter as it is of galaxies. If the dark matter distribution differs from the galaxy distribution, this would indicate that the process suppressing galaxy formation in the void does not affect dark matter, which would be consistent with standard models where galaxies form in dark matter halos, but the halos themselves exist even in underdense regions. If the dark matter distribution matches the galaxy distribution, both being severely depleted, this would suggest that the entire region is underdense in all forms of matter, which is what standard void formation mechanisms predict. To date, weak lensing measurements of the Boötes Void have not been published with sufficient signal-to-noise to draw firm conclusions. The void's distance and the weakness of the lensing signal make this a difficult measurement. Future surveys with wider coverage and deeper imaging may succeed where current surveys have not. The Vera C. Rubin Observatory, currently under construction, will conduct the legacy survey of space and time, imaging billions of galaxies over half the sky. This dataset will enable weak lensing measurements of voids across the universe, including the Boötes Void, with unprecedented precision. Similarly, upcoming spectroscopic surveys, such as those planned for the Dark Energy Spectroscopic Instrument and the European Space Agency's Euclid mission, will measure redshifts for tens of millions of galaxies, mapping the three-dimensional structure of the universe in far greater detail than currently available. These datasets will allow the identification and characterization of large voids across cosmic history, revealing how voids form and evolve over time. If Boötes-like voids are found to be more common than currently thought, this would reduce the statistical tension with lambda CDM. If they remain rare, the tension persists. The Boötes Void also serves as a laboratory for studying the physics of galaxy formation in extreme environments. Most galaxies form in regions of average or above average density, where gas is abundant and gravitational potential wells are deep. The physics of star formation, gas cooling, supernova feedback, and black hole growth are studied primarily in these typical environments. But galaxy formation in voids operates under different conditions. Gas densities are lower. Gravitational potential wells are shallower. Mergers between galaxies are rarer because there are fewer galaxies to merge with. These differences could lead to galaxies with different properties, or they could reveal which aspects of galaxy formation are universal and which are environment-dependent. Studies of void galaxies in general, not just those in the Boötes Void, have found some interesting trends. Void galaxies tend to be bluer and have higher specific star formation rates than galaxies in denser environments. This is consistent with void galaxies being less evolved, having experienced fewer interactions and less environmental quenching of star formation. They are, in a sense, closer to the idealized picture of isolated galaxy evolution, where a galaxy forms stars from its gas reservoir without significant external influence. However, the galaxies in the Boötes Void do not appear to be systematically different from void galaxies elsewhere. This suggests that the extreme underdensity of the Boötes Void affects the number of galaxies that form, but not necessarily the properties of the galaxies that do form. The galaxies that manage to form in the void do so through the same mechanisms that operate in less extreme voids. They are simply much rarer. This rarity itself is the anomaly. Why did galaxy formation fail so completely in this particular region? The standard answer is that the region was initially more underdense than average, and that underdensity was amplified by cosmic expansion until the local density was too low for gas to collapse efficiently into galaxies. But this standard answer requires the initial underdensity to be quite extreme, and it requires that no compensating mechanisms, such as late-time accretion of matter from surrounding regions, filled in the void over time. Cosmic evolution is a dynamic process. Structure grows with time. Voids expand, but they do not remain completely empty forever. Small-scale fluctuations within voids can collapse locally. Gas can be accreted from the edges of voids. Over billions of years, voids gradually fill in, becoming less empty than they were at earlier times. Simulations show this process occurring. The question is whether the Boötes Void has had enough time to fill in, given its current age, or whether it remains as empty as it was at earlier epochs. The age of the void is not straightforward to define. The void exists now, at redshift 0, but it formed over time as the universe expanded. The initial underdensity that seeded the void existed at the time of recombination, when the CMB was formed. That underdensity grew over billions of years as matter drained toward surrounding overdense regions. At some point, the void transitioned from being slightly underdense to being very underdense, and galaxy formation within it effectively ceased. Determining when that transition occurred requires reconstructing the void's history, which in turn requires understanding the initial conditions and the subsequent evolution of structure. One way to probe this is to study the ages of the galaxies within the void. If the galaxies are old, with stars that formed billions of years ago, this suggests that galaxy formation occurred early in the void's history, when the density was higher than it is now. If the galaxies are young, with stars that formed recently, this suggests that galaxy formation has continued over time, albeit at a low rate. Spectroscopic observations that measure stellar ages indicate a mix of both old and young galaxies within the Boötes Void, similar to void galaxies elsewhere. This suggests that galaxy formation in the void was not confined to a single early epoch, but has been an ongoing process, though at a much lower rate than in denser regions. This ongoing formation is itself somewhat surprising in the context of the void's extreme emptiness. If the void is as underdense as the galaxy count suggests, the rate of gas accretion onto dark matter halos should be very low, and the rate of galaxy formation should be correspondingly low. Yet galaxies do exist, and some of them show signs of recent star formation. This implies that either the gas density in the void is higher than the galaxy count would suggest, with much of the gas remaining uncollapsed, or that the galaxies are more efficient at forming stars from the limited gas available to them. Gas observations provide a way to test this. In addition to galaxies, which are concentrations of stars, gas, and dark matter, the cosmic web also contains diffuse gas in the intergalactic medium. This gas is difficult to observe directly because it is hot and diffuse, but can be detected through its absorption of light from background quasars. By measuring the absorption spectra of quasars located behind the Boötes void, the amount and distribution of gas within the void can be inferred. Such observations have been conducted, but the number of suitable background quasars is limited, and the results are uncertain. Some studies suggest that the gas content of the void is lower than average, consistent with the galaxy deficit. Others suggest that the gas content is closer to average, implying that the deficit is specifically in galaxies, not in all baryonic matter. If the gas content is closer to average while the galaxy content is severely depleted, this would indicate that the process suppressing galaxy formation in the void is not a lack of raw material, but rather an inefficiency in converting gas into stars. This could be due to a lack of dense dark matter halos, which are the sites where gas collapses to form galaxies. If the void is underdense in dark matter, it would be underdense in dark matter halos, and thus underdense in galaxies, even if diffuse gas remains. This is consistent with the standard picture of void formation, where both dark matter and gas are depleted in voids, but the depletion affects the collapsed structures more than the diffuse components. Alternatively, if the gas content is also severely depleted, matching the galaxy deficit, this would suggest that the void is underdense in all components, which is also consistent with standard models, but requires an even more extreme initial underdensity. Distinguishing between these scenarios requires more detailed observations of the gas distribution in the void, which is a target for future missions. The Boötes void is not the only large void known, but it is among the most studied due to its extreme properties and its proximity. Other large voids have been identified in galaxy surveys, including voids in the local universe similar in size to the Boötes void and voids at higher redshift seen in the distribution of galaxies in deep surveys. These voids provide a broader context for understanding the Boötes void. If all large voids have similar properties, then the Boötes void is simply one example of a common class of structures. If the Boötes void is unusual even among large voids, its anomaly is more pronounced. Comparative studies of large voids suggest that there is a continuum of properties. Some voids are large, but not very empty. Some are very empty, but not very large. The Boötes void is unusual in being both large and empty, but it is not completely unique. A few other voids with comparable properties have been identified, though none that clearly exceeded on both metrics simultaneously. This suggests that the Boötes void is at the extreme end of a distribution, rather than being an isolated outlier. This brings the discussion back to statistics. If the Boötes void is at the extreme end of a distribution predicted by lambda CDM, it is consistent with the standard model, but it is a rare event. The question is how rare, and whether the rarity is surprising given the volume of the observable universe. Answering this question rigorously requires precise measurements of the void's properties, a large sample of voids for comparison, and accurate simulations that predict the distribution of void properties. All three are improving with time, but none are yet perfect. The implications of the Boötes void extend beyond its specific properties. It is a reminder that the universe contains extremes, rare configurations that test the boundaries of what is possible within the laws of physics. These extremes are valuable because they provide the strongest tests of theory. A theory that explains only typical structures is incomplete. A theory that explains typical structures and extreme structures is robust. The Boötes void is one of those extreme structures. If it can be explained within lambda CDM, the model is stronger for it. If it cannot, the model must be revised. The process of scientific inquiry is inherently iterative. Observations suggest a phenomenon. Theory attempts to explain it. Further observations test the explanation. The explanation is refined or replaced. The Boötes void is embedded in this process. It was discovered by accident as a blank region in a redshift survey. It was recognized as unusual, prompting theoretical work to explain it. The initial explanations invoked void merger, which is consistent with standard models. Subsequent observations revealed the tube structure, which is less easily explained by a simple merger. Simulations attempted to reproduce the void's properties with mixed success. More observations and better simulations are planned. The process continues. This iterative process is slow, constrained by the time required to build telescopes, conduct surveys, run simulations, and analyze data. But it is also cumulative. Each generation of observations and simulations builds on the previous one, gradually reducing uncertainties and sharpening the picture. The Boötes Void is better understood now than it was in 1981, but is not yet fully understood. The understanding will continue to improve as long as astronomers and cosmologists continue to study it. One of the challenges in studying the Boötes Void is its location on the sky. The constellation Boötes is visible from the northern hemisphere and is well placed for observation during certain times of the year, but the void itself spans a large angular region, requiring wide-field surveys to map comprehensively. Many of the large galaxy surveys have included the region of the Boötes Void in their coverage, but the depth and completeness of these surveys vary. Deeper surveys are needed to detect fainter galaxies and to measure their properties accurately. The depth of a survey is determined by the sensitivity of the telescope and the total exposure time. Fainter galaxies require longer exposures to detect. The Boötes Void, being very distant, contains galaxies that are intrinsically faint and made even fainter by their distance. Detecting these galaxies requires large telescopes and long exposures. The 60 galaxies currently known in the void are the brightest ones, the ones that were easiest to detect. There may be additional fainter galaxies that have not yet been detected. If the true number of galaxies is significantly higher than 60, the void becomes less unusual and the tension with lambda CDM decreases. However, follow-up surveys specifically targeting the Boötes Void with sensitive instruments have been conducted, and the galaxy count has not increased dramatically. This suggests that the 60 galaxy number is reasonably complete down to a certain luminosity threshold, and that the deficit is real, but does not rule out the presence of very faint dwarf galaxies below the detection threshold. Dwarf galaxies are intrinsically faint and could be numerous in voids without being easily detectable. If the void contains a large population of undetected dwarf galaxies, the total mass in galaxies would be higher than the count of 60 suggests, and the void would be less empty than it appears. This touches on a broader issue in galaxy surveys: the relationship between the number of galaxies detected and the total mass in galaxies. Luminosity functions, which describe the distribution of galaxy luminosities, show that there are many more faint galaxies than bright galaxies. The faint end of the luminosity function is steep, meaning that small decreases in luminosity correspond to large increases in number. Surveys that are sensitive only to bright galaxies miss the majority of the galaxy population by number, though not necessarily by mass, since faint galaxies contribute little to the total stellar mass. For the Boötes Void, the question is whether the 60 detected galaxies represent the entire galaxy population or just the bright end. If they represent the entire population, the deficit is as extreme as it appears. If they represent only the bright end, and there's a large population of faint galaxies, the deficit is less extreme. Observational efforts to detect faint galaxies in the void are ongoing, using deep imaging and spectroscopy, but the results so far do not indicate a large hidden population. The void appears to be genuinely empty, not just apparently so. Another aspect of the Boötes Void that merits consideration is its role in larger-scale cosmic flows. Voids are not static. They are embedded in the Hubble flow, the overall expansion of the universe, but they also participate in peculiar velocities driven by local gravitational fields. Large-scale structures, such as the Great Attractor and the Shapley concentration, exert gravitational pulls on surrounding matter, including voids. The motion of the local group of galaxies, which includes the Milky Way, is influenced by these large-scale flows. The Boötes Void, being a large structure, also influences the flow, acting as a repulsive void that pushes matter away. Mapping these flows requires measuring the peculiar velocities of galaxies, which is done by comparing their observed redshifts to the expected redshifts from the Hubble flow. Deviations indicate motion toward or away from nearby structures. Such measurements have been made for galaxies around the Boötes Void, confirming that the void is a repulsive structure in the flow field. This is consistent with the void being a real underdensity, not an artifact of the survey. However, the measurements are noisy, and the flow field is complex with contributions from multiple structures. Disentangling the specific contribution of the Boötes Void from the overall flow is challenging. The void's influence on the flow field depends on its mass deficit. A void with a large mass deficit exerts a strong repulsive effect. A void with a small mass deficit exerts a weak effect. By measuring the strength of the repulsion, the mass deficit can be inferred. This provides an independent estimate of the void's properties, complementing the galaxy count. So far, the flow measurements are consistent with the void having a large mass deficit, in line with the galaxy deficit, but the uncertainties are large enough that alternative interpretations remain possible. The Boötes Void also raises questions about the predictability of cosmology. Cosmological models are deterministic in the sense that given a set of initial conditions and physical laws, the evolution of structure follows uniquely. But the initial conditions themselves are stochastic, drawn from a probability distribution. This means that cosmology is ultimately a statistical science. The theory predicts distributions of outcomes, not specific outcomes. The Boötes Void is one specific outcome, a particular realization of structure formation in one particular region of one particular universe. In a different realization, with different initial conditions drawn from the same distribution, the Boötes Void would not exist. A different pattern of voids and filaments would emerge. This is not a failure of the theory. It is inherent in the nature of the theory as a statistical framework. The theory does not predict that the Boötes Void will exist. It predicts the probability that a void like the Boötes Void will exist somewhere in a volume like the observable universe. The distinction is subtle but important. This statistical nature of cosmology means that claims about the significance of anomalies like the Boötes Void must be probabilistic. The void is not in contradiction with lambda CDM. It is improbable within lambda CDM. The degree of improbability determines whether the void is a mere curiosity or a genuine challenge. Quantifying that degree of improbability requires large simulations and careful statistical analysis, both of which are ongoing. One of the tools used in this analysis is the concept of cosmic variance. Even if the universe as a whole is well described by a statistical model, any finite region of the universe will exhibit fluctuations around the mean predicted by the model. These fluctuations are not measurement errors. They are intrinsic to the statistical nature of structure formation. Cosmic variance sets a fundamental limit on how well the properties of the universe can be inferred from observations of a finite region. For the Boötes Void, cosmic variance means that the observed properties of the void fluctuate around the mean properties predicted by lambda CDM. The question is whether the observed properties are within the expected fluctuation range. If they are, the void is consistent with lambda CDM. If they are not, the void is anomalous. But cosmic variance is largest on the largest scales because there are fewer independent structures on large scales. The observable universe contains only a finite number of void-scale structures, so the cosmic variance for voids is significant. This makes it difficult to draw definitive conclusions from a single void, no matter how extreme it appears. To reduce cosmic variance, a large sample of voids is needed. By studying many voids, their collective properties can be averaged, reducing the impact of fluctuations in any one void. This is one of the goals of ongoing and future galaxy surveys. By mapping the universe in great detail over large volumes, thousands of voids can be identified and studied. The statistical properties of this void population can then be compared to simulation predictions with much greater confidence than is possible from studying the Boötes Void alone. Early results from such studies suggest that the population of voids observed in the universe is broadly consistent with lambda CDM predictions. Most voids have properties that fall within the expected range. A few, including the Boötes Void, have properties that are at the edge of the expected range. The question is whether these edge cases are statistical flukes, expected in a large sample, or whether they indicate a systematic deviation from model. Answering this question requires precise measurements and careful statistics. The measurements must account for observational biases, such as the tendency for surveys to be less complete in certain regions or at certain magnitudes. The statistics must account for the correlations between voids, because voids are not independent structures. They are connected through the cosmic web, and their properties are influenced by their surroundings. Ignoring these correlations can lead to underestimating the uncertainties and overestimating the significance of apparent anomalies. These technical challenges are being addressed by cosmologists through increasingly sophisticated analysis techniques. Bayesian inference, which combines observed data with prior knowledge in a principled way, is used to estimate void properties and their uncertainties. Mock catalogs, simulated galaxy surveys that mimic the properties of real surveys, are used to test analysis methods and quantify biases. Machine learning techniques are being explored to identify voids in large data sets and to characterize their properties efficiently. Despite these advances, the question of whether the Boötes Void is truly anomalous remains open. The void is extreme. It is at the tail of the distribution. But tails exist. Rare events happen. The challenge is determining whether the void is rare within the expected distribution or rare beyond it. One way to frame this is to ask how many universes one would need to simulate to find a Boötes-like void. If the answer is 10 universes, the void is not particularly surprising. If the answer is 1,000,000 universes, the void is very surprising. Current simulations suggest a number somewhere in between, perhaps a few hundred to a few thousand. This makes the void unusual but not impossible within lambda CDM. However, this estimate depends on the definition of Boötes-like. If the definition includes only the size and the galaxy count, the void is less rare. If it also includes the tube structure and the specific configuration of surrounding superclusters, it is more rare. The more specific the definition, the rarer the structure. This is inevitable because more constraints reduce the probability space. But it also means that the significance of the void depends on which features are considered essential and which are incidental. This ambiguity is part of why the Boötes Void remains a subject of debate. Different researchers emphasize different features and arrive at different conclusions about its significance. Some view it as a clear indication that lambda CDM is incomplete, at least in its simplest form. Others view it as a rare but expected structure that demonstrates the richness of the cosmic web. Both views are represented in the literature, and neither has definitively prevailed. The debate is healthy. It drives further research, prompts new observations, and motivates refined simulations. The Boötes Void serves as a focal point for broader questions about the nature of cosmic structure and the limits of current models. Even if the void is ultimately shown to be consistent with lambda CDM, the effort to understand it will have deepened our knowledge of structure formation and tested the model in ways that might not have occurred otherwise. The void also serves as a reminder of the scale of the universe. 330 million light-years is a distance so vast that it defies human intuition. Light, traveling at the fastest speed possible, takes 330 million years to cross the void. The photons we detect from galaxies on the far side of the void began their journey before the first dinosaurs walked the Earth. The void itself has existed as a coherent structure for billions of years, slowly evolving as the universe expands. Yet despite its scale, the void is only a small part of the observable universe. The observable universe extends to a distance of about 46 billion light-years, encompassing countless galaxies, clusters, filaments, and voids. The Boötes Void is one structure among billions. Its extreme nature makes it noteworthy, but it is not unique in being noteworthy. The universe is full of extremes, each with its own story, each pushing the boundaries of what is known and understood. The study of the Boötes Void is part of the broader enterprise of cosmology the attempt to understand the universe as a whole, its origin, its evolution, its structure, and its fate. Cosmology has made remarkable progress over the past century, from the discovery of the expanding universe to the establishment of the Big Bang model to the identification of dark matter and dark energy. The lambda-CDM model represents the culmination of this progress, a coherent framework that explains the vast majority of observations with remarkable precision. But cosmology is not complete. Questions remain. Dark matter has not been directly detected. Dark energy is not understood. The initial conditions set by inflation are inferred, but not confirmed. The formation of the first stars and galaxies is still being pieced together. The ultimate fate of the universe is uncertain, and structures like the Boötes Void hint that there may be more complexity in the cosmic web than current models fully capture. The void is a window into this complexity. It is a place where the universe did something unexpected, or at least something rare. By studying what happened there, why it happened, and how it fits into the broader pattern of structure formation, cosmologists gain insight into the fundamental processes that shape the cosmos. The void is not just an empty region. It is a laboratory, a test case, a challenge, and a mystery. It represents both what is known and what remains unknown about the universe. As observations continue and simulations improve, the understanding of the Boötes Void will continue to evolve. New data may reveal features that are currently hidden. New simulations may show that structures like the void are more common or more naturally produced than currently thought. Or new data may show that the void is even more extreme than currently measured, pushing it further into the regime where standard models struggle to explain it. The future of the void story is unwritten, shaped by the ongoing efforts of astronomers and cosmologists around the world. What is clear is that the void matters. It is not a trivial feature that can be ignored. It is a large-scale structure with properties that sit at the edge of current understanding. It demands explanation, and the explanation must be consistent with everything else that is known about the universe. This is the challenge that the Boötes Void poses, and it is a challenge that continues to drive research. The void's existence also prompts broader philosophical reflections on the nature of emptiness and absence. In human experience, absence is often defined by what is not there rather than by what is. A void is notable because galaxies are missing, not because space itself has any special property. But in cosmology, absence can be as informative as presence. The distribution of voids, their sizes, their shapes, their emptiness, all carry information about the underlying physics of structure formation. Studying what is not there is as important as studying what is. This inversion of focus from presence to absence is characteristic of much of modern cosmology. Dark matter is inferred from its gravitational effects, not from direct detection. Dark energy is inferred from the acceleration of expansion, not from direct observation. Voids are mapped by the absence of galaxies, not by the presence of any tangible structure. Cosmology is, in many ways, the study of what cannot be seen directly, inferred from its effects on what can be seen. The Boötes Void exemplifies this approach. The void itself is not an object. It is a region where objects are scarce. Its properties are defined by subtraction, by measuring how much less there is compared to what is expected. This requires a baseline, an expectation derived from theory and from measurements of other regions. Without that baseline, the void would not be recognizable as unusual. It would simply be a region of space like any other. The baseline is provided by lambda-CDM and by surveys of the cosmic web. These establish what a typical region of space looks like at a given distance and on a given scale. The Boötes Void deviates from that baseline. The deviation is what makes it interesting. But the deviation is only meaningful in the context of the baseline. If the baseline is incorrect, the deviation may not be real. If the baseline is correct, the deviation is real and demands explanation. This interdependence between observation and theory is fundamental to science. Observations are interpreted in the context of theory. Theory is tested against observations. Neither stand alone. The Boötes Void is a test of lambda-CDM. Lambda CDM is the framework used to interpret the Boötes Void. The relationship is circular, but productively so. Each informs the other, and the result is a gradually improving understanding of both the specific phenomenon and the general principles. The void also highlights the importance of surveys. Without systematic mapping of the galaxy distribution over large volumes, the void would not have been discovered. Serendipitous discoveries are valuable, but systematic surveys are essential for understanding the universe as a whole. They provide the context in which individual discoveries can be interpreted. They reveal the statistical distribution of structures, allowing rare outliers like the Boötes Void to be recognized as such. The history of cosmology is, to a large extent, the history of surveys. Each generation of surveys has mapped the universe more completely, revealing new structures and new phenomena. The first surveys, conducted photographically in the early 20th century, revealed the clustering of galaxies. Later surveys, conducted spectroscopically to measure redshifts, revealed the three-dimensional structure of the cosmic web. Modern surveys, conducted with digital detectors on large telescopes, are revealing the universe in unprecedented detail, probing fainter galaxies, more distant epochs, and larger volumes. Each new survey has the potential to discover new structures like the Boötes Void, or to refine the understanding of known structures. Future surveys, with wider coverage, greater depth, and more complete spectroscopy, will continue this tradition. They will map billions of galaxies over billions of light years, creating a comprehensive picture of the cosmic web and its evolution over cosmic time. In this picture, the Boötes Void will be one structure among many, a particularly extreme example of a common class of features. But even as the void becomes part of a larger statistical picture, its individual properties will remain important. It is one of the closest and largest supervoids, making it a prime target for detailed study. Its proximity allows observations with higher signal-to-noise and finer resolution than is possible for more distant voids. Its size makes it a significant feature in the cosmic web, with measurable effects on the surrounding structures and potentially on the cosmic microwave background. Its extreme emptiness makes it a stringent test of structure formation models. These attributes ensure that the Boötes Void will remain a focus of research for years to come. New telescopes will observe it. New simulations will attempt to reproduce it. New theoretical ideas will attempt to explain it. The void will continue to challenge and inform cosmology, serving as a benchmark against which models are tested and refined. In this sense, the void is not just a region of space. It is a scientific object, a subject of inquiry, a source of data and insight. It exists independently of human observation, but its significance is constructed through the process of scientific investigation. The void is what it is, a nearly empty region of space 330 million light-years across. But it is also what scientists make of it, a puzzle, a test, a mystery that drives the search for deeper understanding. The search for that understanding proceeds incrementally, through the accumulation of data, the refinement of models, and the testing of hypotheses. There are no sudden breakthroughs, no single observations that definitively solve the puzzle. Instead, there's a gradual convergence toward consensus as the weight of evidence shifts in favor of one interpretation or another. The Boötes Void is in the midst of this process, neither fully explained nor fully mysterious, but somewhere in between, a structure that is understood in broad outline, but not in every detail. The broad outline is clear. The void is a large, empty region formed through the gravitational dynamics of structure formation in an expanding universe. It is underdense in both dark matter and galaxies. It is surrounded by superclusters that drain matter from it over billions of years. It contains a small number of galaxies arranged in a tube-like structure, possibly representing a residual filament. These features are consistent with lambda CDM, but they push the boundaries of what the model naturally produces. The details are less clear. Why is the void so empty, with only 60 galaxies instead of few hundred? Why are those galaxies arranged in a tube? Is the tube a single coherent structure or a chance alignment of multiple smaller structures? Is the void's extreme emptiness a result of rare initial conditions? Or is there some process that suppressed galaxy formation beyond what standard models predict? These questions remain open, and answering them requires more data and more detailed simulations. The data are coming. New surveys are underway. The Sloan Digital Sky Survey has completed multiple phases, mapping millions of galaxies. The Dark Energy Survey has imaged hundreds of millions of galaxies over a large area of the southern sky. The Dark Energy Spectroscopic Instrument is measuring redshifts for tens of millions of galaxies. The Vera Rubin Observatory will begin operations soon, imaging the entire visible sky repeatedly and detecting billions of galaxies. The Euclid satellite, launched by the European Space Agency, is mapping the geometry and distribution of matter across the universe. The Nancy Grace Roman Space Telescope, planned by NASA, will conduct wide-field infrared surveys that will complement the ground-based surveys. Each of these surveys will contribute to the understanding of the Boötes Void. They will detect fainter galaxies within the void, reducing the uncertainty in a galaxy count. They will map the distribution of galaxies around the void, clarifying its relationship to surrounding structures. They will measure the properties of void galaxies in detail, revealing their star formation histories, their metallicities, and their kinematics. They will provide weak lensing measurements that probe the distribution of dark matter in and around the void. They will measure the integrated Sachs-Wolf effect, if it exists, providing an independent confirmation of the void's underdensity. The simulations are also improving. Computational power continues to increase, allowing larger volumes and higher resolution. New algorithms are being developed that can model galaxy formation physics more accurately. Machine learning techniques are being applied to accelerate simulations and to extract patterns from simulation data. These advances are enabling simulations that can resolve both the cosmic web on the largest scales and individual galaxies on the smallest scales, bridging the dynamic range that has historically been a barrier. With larger simulations, the statistics of rare structures like the Boötes Void can be characterized more precisely. The simulations can produce thousands of voids, and the properties of these simulated voids can be compared to the observed void with statistical rigor. If the Boötes Void falls within the distribution of simulated voids, it is consistent with lambda CDM. If it falls outside, it is anomalous. The simulations provide the distribution. The observations provide the data point. The comparison reveals whether the data point is consistent with the distribution. This comparison is not simple, because the properties of voids are multidimensional. Size, emptiness, shape, internal structure, surrounding structures, all must be considered. A void could be typical in one property and atypical in another. The challenge is to define a metric that captures the overall degree of typicality, accounting for correlations between properties. This is an active area of research, with different groups proposing different metrics and different statistical approaches. One approach is to use the likelihood of observing a void with the Boötes Void's properties given the lambda CDM model. If the likelihood is high, the void is consistent with the model. If the likelihood is low, the void is inconsistent. The likelihood is calculated by running many simulations, counting how often voids with similar properties appear, and normalizing by the total number of simulations. This gives a probability, which can be compared to a threshold to determine statistical significance. Another approach is to use machine learning to classify voids. A machine learning algorithm is trained on simulated voids to recognize the typical range of properties. The algorithm is then applied to the observed Boötes Void to determine whether it is classified as typical or atypical. If the algorithm consistently classifies the void as atypical, this suggests that it falls outside the range of what the model naturally produces. If the algorithm classifies it as typical, this suggests that it is consistent with the model, even if it is rare. Both approaches have strengths and weaknesses. The likelihood approach is transparent and grounded in statistical theory, but it requires defining what similar properties means which involves subjective choices about which properties to include and how to weight them. The machine learning approach can discover patterns in high-dimensional data without requiring explicit definitions. But it is a black box, and it can be difficult to interpret why the algorithm makes a particular classification. Despite these challenges, progress is being made. The consensus is gradually shifting as more data and more simulations become available. The current consensus is that the Boötes Void is unusual but not impossible within Lambda CDM. It is at the tail of the distribution, but it is not so far out on the tail that it requires new physics. However, this consensus is not unanimous, and it may shift as new results become available. The void is also being studied in the context of other cosmological anomalies. The Hubble tension, the mismatch between different measurements of the expansion rate, has prompted interest in whether local voids could affect distance measurements. If the local group resides in a large void, the local expansion rate could differ from the global average, potentially explaining the tension. This has led to searches for large voids in the local universe, including attempts to characterize the local void. The Boötes Void, being farther away, does not directly affect local measurements, but it provides a comparison point for understanding how voids influence their surroundings. Similarly, the sigma-8 tension, the mismatch between measurements of the amplitude of matter clustering, has prompted interest in whether voids are more or less common than Lambda CDM predicts. If voids are more common, this could indicate that structure formation is less efficient than the model predicts, reducing the amplitude of clustering. If voids are less common, this could indicate the opposite. The Boötes Void, being an extreme example, is relevant to this question, though its single existence does not settle it. These connections between different anomalies suggest that the Boötes Void may be part of a broader pattern of tension between observations and Lambda CDM. Individually, no single anomaly is definitive. Collectively, they raise questions about whether the model is missing some important physics. Resolving these tensions is one of the major goals of cosmology in the coming decades. The Boötes Void will play a role in this resolution, whether it turns out to be consistent with Lambda CDM or not. If it is consistent, it will serve as an example of how rare structures can arise naturally within the standard model, demonstrating the richness of the cosmic web. If it is inconsistent, it will provide crucial evidence for new physics, pointing the way toward a more complete theory of structure formation. Either way, the void is valuable. The scientific value of the void lies not in its emptiness per se, but in what that emptiness reveals about the underlying physics. Voids are not merely gaps in the distribution of galaxies. They are regions where the processes of structure formation operated under extreme conditions, conditions that test the limits of current models. By studying these extreme conditions, scientists learn about the range of behavior that the models can produce, and they identify the boundaries beyond which new physics is required. The Boötes Void is one such boundary. It may not be the boundary where new physics is definitively required, but it is close. It is a place where the models are stretched, where the predictions are uncertain, where the observations are challenging. It is a place where science operates at the frontier, grappling with the limits of knowledge and pushing toward deeper understanding. This frontier is not static. It moves as knowledge advances. What was once a mystery becomes understood. What was once unexplained becomes explained. The Boötes Void may one day be fully explained, its properties no longer puzzling, its place within Lambda CDM secure. Or it may remain a mystery, a persistent anomaly that hints at physics beyond the current paradigm. Only time and continued research will reveal which of these futures unfolds. In the meantime, the void exists, silent and vast, a nearly empty region of space that has become one of the most intensely studied structures in cosmology. It is a testament to the power of observation, the importance of systematic surveys, and the human drive to understand the universe. It is a reminder that the universe contains wonders that challenge intuition and defy expectation. It is a structure that should not be as extreme as it is, according to the baseline of current understanding, yet it is. This tension between observation and expectation is the engine of scientific progress. Without tension, there is no motivation to refine theories or to conduct new observations. The Boötes Void creates tension. It poses questions. It demands answers. In doing so, it drives the field forward, ensuring that cosmology remains a vibrant and evolving science, rather than a static body of accepted truths. The void's role in this process will continue for as long as questions remain. And questions do remain, despite decades of study. The tube structure is still not fully explained. The extreme emptiness is still at the edge of what models comfortably produce. The relationship between the void and surrounding superclusters is still being mapped. The implications for galaxy formation in underdense environments are still being explored. Each of these questions is a thread that, when pulled, may unravel new insights into the nature of the cosmos. The cosmos, after all, is not obligated to conform to human expectations. It is what it is, governed by laws that humans strive to discover and understand. The Boötes Void is a manifestation of those laws, an outcome of processes that operated over billions of years and across hundreds of millions of light years. Understanding the void means understanding those processes, which in turn means understanding the fundamental physics of gravity, dark matter, dark energy, and the formation of structure from primordial fluctuations. This understanding is hard-won. It requires building telescopes that can detect faint galaxies at great distances. It requires developing algorithms that can process vast datasets. It requires running simulations on supercomputers for months at a time. It requires theoretical work to interpret the results and to make predictions. It requires collaboration among scientists across institutions and countries. It requires patience, persistence, and a willingness to grapple with uncertainty. The Boötes Void embodies all of these challenges. It is a distant structure, difficult to observe in detail. It is rare, making statistical analysis challenging. It is large, requiring simulations with vast dynamic range. It is complex, with multiple properties that must be explained simultaneously. It is at the edge of current understanding, where models are uncertain and predictions are probabilistic. It is, in short, a worthy subject of scientific inquiry, a problem that tests the full range of techniques and approaches available to modern cosmology. And so the inquiry continues, driven by curiosity about this vast, empty region in the direction of Boötes the herdsman. The inquiry will continue until the void is understood, or until it becomes clear that understanding the void requires rethinking fundamental aspects of cosmology. Either outcome advances knowledge. Either outcome is valuable. The journey toward that outcome is the essence of science. The void waits, unchanged by human investigation, a structure formed billions of years ago that will persist for billions of years to come. It does not care whether it is understood. It does not care whether it is consistent with lambda CDM. It simply exists, a nearly empty region of space, a testament to the stochastic nature of structure formation and the vast scales on which the universe operates. Its existence alone is remarkable. The fact that it can be studied, its properties measured, its implications debated, is a testament to the reach of human inquiry and the power of the scientific method. In that sense, the Boötes Void is not just a cosmological phenomenon. It is a meeting point between the universe and the human mind, a place where the objective reality of physical processes encounters the subjective drive to comprehend. The void is indifferent to this encounter, but the encounter transforms the void from a mere region of space into a scientific object, laden with meaning and significance, a puzzle whose solution may illuminate the deepest workings of the cosmos. That transformation is ongoing. The void remains partially understood, partially mysterious. New observations add detail. New simulations add context. New theoretical ideas add perspective. The picture grows clearer, but clarity is never complete. There's always more to learn, always deeper questions to ask, always further refinement to pursue. The Boötes Void is a reminder that the universe is not a closed book with a final page. It is an open question, an ongoing story, a field of inquiry that extends indefinitely into the future. The Void story is part of that larger story, the story of the universe itself, from the Big Bang to the present, from the first quantum fluctuations to the vast cosmic web, from the formation of the first stars to the eventual fate of all structure. Understanding the void is understanding a chapter of that story, a chapter about how empty regions form, how they evolve, how they influence their surroundings, and what they reveal about the fundamental laws of nature. That chapter is still being written in the observations of telescopes pointed toward Boötes, in the output of simulations running on supercomputers, in the equations derived by theorists, in the debates conducted at conferences, and in journals. Each contribution adds a sentence, a paragraph, a page. The chapter grows longer, more detailed, more complete, but is not yet finished. The Boötes Void still holds secrets. It still poses questions. It still challenges understanding. And that is as it should be. The universe is vast and complex. Complete understanding may be unattainable, but the pursuit of understanding is not. The pursuit is what drives science forward, what transforms curiosity into knowledge, what turns observations into insight. The Boötes Void is an object of that pursuit, a target of inquiry, a focus of attention. It deserves that attention because it is extreme, because it is puzzling, because it sits at the boundary of what is known. Boundaries are where progress happens. They are where the known meets the unknown, where certainty gives way to uncertainty, where models are tested most stringently. The Boötes Void is such a boundary, a structure that is almost explained but not quite, almost understood but not fully, almost consistent with theory but not comfortably. It is a place of tension, and tension drives resolution. The resolution may come from observations, from simulations, from theory, or from some combination of all three. It may come quickly in the next few years, as new surveys deliver data and new simulations deliver predictions. Or it may come slowly, over decades, as understanding gradually deepens and uncertainties gradually shrink. The pace of progress is unpredictable, determined by the difficulty of the problem and the resources available to address it. But progress is inevitable. Science is cumulative. Each generation builds on the work of the previous one. The Boötes Void, discovered in 1981, has been studied ever since. The studies have produced insights, even if they have not produced a complete explanation. Those insights will inform future studies, which will produce further insights, until eventually the void is understood as well as the limitations of observation and theory allow. That understanding will not diminish the void's significance. If anything, it will enhance it. A structure that is understood is no less remarkable than one that is mysterious. The Boötes Void, once fully explained, will stand as an example of how extreme structures arise naturally from the laws of physics, or as an example of how those laws must be extended to account for phenomena that the simplest models do not predict. Either way, the void will have served its purpose, challenging and informing the science of cosmology, driving the pursuit of knowledge about the universe and its contents. The pursuit continues. The void remains. The questions persist. The answers, partial and incomplete, accumulate. In the story of the Boötes Void, a nearly empty region 330 million light-years across, containing only 60 galaxies arranged in a tube through a space that should hold 2,000, continues to unfold. One observation, one simulation, one theoretical insight at a time, moving always toward deeper understanding, toward a more complete picture of the cosmic web and the processes that shaped it, toward the resolution of tensions between what is observed and what is expected, toward the boundary where current models either succeed or fail, and where new physics either emerges or retreats back into the realm of speculation.